A single wind turbine can generate enough electricity in just one day to help power up to 100,000 people under ideal conditions. That's a staggering amount of energy from nothing more than moving air. Most people see wind turbines as giant fans spinning lazily on the horizon. But hidden inside these towering machines is one of the most sophisticated energy systems ever created. These giants stand nearly 200 meters tall, have blades longer than a football field, survive hurricane-force winds, and can operate continuously for decades. But how exactly do they turn wind into electricity? How much power do they really produce? And could wind turbines eventually replace traditional power plants? Today, we're climbing inside one of humanity's most impressive machines to discover how wind becomes electricity. Imagine driving through the countryside. In the distance, you notice several white structures slowly rotating against the sky. At first glance, they don't seem particularly impressive, but that's because your brain struggles to process their true scale. The tip of a modern wind turbine blade can travel at speeds exceeding 250 kilometers per hour, faster than many high-speed trains. Yet from the ground, it appears almost lazily. Walk closer. At about 100 meters from the tower, each passing blade creates a noticeable pulse of air. Suddenly, the turbine feels less like a piece of infrastructure and more like a gigantic machine in motion. Modern offshore turbines can reach nearly 200 meters from base to blade tip. Their rotor diameter exceeds 150 meters. For comparison, a Boeing 747 has a wingspan of about 68 meters. That means a single turbine blade can be longer than the entire wingspan of one of the world's most iconic jumbo jets. And despite their enormous size, these blades are engineered with incredible precision. Many people assume wind simply pushes the blades around. In reality, that's not how most of the power is generated. A turbine blade is designed much like an airplane wing. One side is curved while the other's flatter. As wind flows around the blade, air moves faster over the curved surface, creating a low pressure zone. The pressure difference creates lift. It's the exact same aerodynamic principle that allows airplanes to leave the ground. This lift force pulls the blade forward and causes the rotor to spin. That's why wind turbines can continue generating electricity even when winds aren't particularly strong. They're not just being pushed by the wind, they're flying through it. Modern turbine blades are made from fiberglass and carbon fiber composites. They're lightweight yet strong enough to withstand enormous forces year after year. Each blade can weigh between 20 and 50 tons. Manufacturing a single blade takes several weeks. Layers of composite material are placed into massive molds, saturated with resin, and cured into a single seamless structure. The finished product contains no internal joints or weak points. That's important because even tiny defects could eventually become catastrophic under constant stress. Transporting these blades is a challenge of its own. Some travel hundreds of kilometers on specialized trucks that move mostly at night. Offshore turbines present an even bigger challenge. Giant installation vessels equipped with cranes taller than many buildings are used to assemble turbines at sea. Under ideal weather conditions, installing one offshore turbine can take just a few days. At the top of the tower sits the nacelle. Think of it as the turbine's engine room. Inside this giant enclosure is where the real magic happens. The challenge engineers face is surprisingly simple. The blades rotate very slowly, usually between 5 and 15 revolutions per minute, but electrical generators typically need to spin hundreds of times faster. So how do you turn a slow rotation into useful electricity? The answer is a gearbox. Inside the nacelle, a series of gears increases the rotational speed from the rotor shaft before transferring it to the generator. In large turbines, these gearboxes can weigh nearly 80 tons and cost millions of dollars. Some modern turbines skip the gearbox entirely. These direct drive systems use specialized generators that produce electricity at lower rotational speeds. They are generally more reliable but significantly heavier. Both approaches are used throughout the industry today. Once the rotation reaches the generator, the process becomes surprisingly familiar. Magnets spin around coils of copper wire. As they rotate, they create an electric current. This phenomenon, known as electromagnetic induction, was discovered by Michael Faraday nearly 200 years ago, and remarkably, it still forms the foundation of nearly every major power plant on Earth. The generated electricity travels down cables inside the tower to a transformer at the base. The transformer increases the voltage so the power can travel long distances with minimal losses before reaching homes and businesses. Wind is unpredictable. It changes speed, it changes direction, and sometimes it becomes dangerously strong. That's why every modern turbine constantly monitors its surroundings. Sensors mounted on the nacelle measure wind conditions every second. When the wind shifts direction, electric motors rotate the entire nacelle so the blades continue facing directly into the airflow. This process is called yaw control. The blades can also rotate along their own axis. This is known as pitch control. When winds are weak, the blades adjust to capture as much energy as possible. When winds become stronger, they change angle to prevent overspeeding. And if wind speeds reach dangerous levels, typically around 25 meters per second, the turbine automatically shuts itself down. The blades rotate edge-on to the wind, eliminating lift and bringing the rotor to a stop. The machine waits until conditions become safe again. Every turbine contains an industrial computer that continuously analyzes information from dozens of sensors. It monitors wind speed, wind direction, blade loads, bearing temperatures, shaft vibrations, power output. If anything exceeds safe limits, the system immediately responds. It can reduce power output, adjust blade angles, or shut the turbine entirely. Modern wind farms containing hundreds of turbines can often be managed remotely by surprisingly small teams. Predictive maintenance software can even estimate when a component is likely to fail before it actually does. That means repairs can be scheduled in advance, reducing downtime and costs. Now for the question everyone wants answered. One of the most powerful wind turbines currently in operation is the Vestas V236. Its rated capacity is an incredible 15 megawatts. Its rotor diameter measures 236 meters. That's longer than 2 football fields placed end to end. Under ideal conditions, a turbine of this size can generate roughly 80 million kilowatt hours of electricity per year. That's enough energy to support tens of thousands of homes. When accounting for residential, commercial, and industrial consumption, one turbine can indirectly serve the electricity needs of around 100,000 people under favorable wind conditions. That's an astonishing amount of energy from a single machine. There's one important catch. Wind turbines don't generate maximum power all the time. Energy experts call this the capacity factor. A turbine only reaches full output when wind conditions are perfect. Over an entire year, most modern turbines produce about 35% to 45% of their theoretical maximum. Offshore turbines often perform better, sometimes approaching 50% thanks to stronger and more consistent winds. Compare that to nuclear power plants, around 90%, coal power plants, around 75%. This doesn't mean wind energy is inferior, it simply operates differently. A coal plant produces electricity whenever fuel is supplied. A wind turbine produces electricity whenever nature cooperates. This question sits at the center of today's energy debate. A large offshore wind farm can generate as much annual electricity as a conventional power station. But unlike traditional plants, wind farms can't decide when the wind blows. That's where energy storage becomes crucial. When production exceeds demand, the extra electricity must be stored. When wind generation falls, stored energy must fill the gap. Without effective storage, renewable energy can never reach its full potential. Several solutions are already being deployed. The most common is pumped hydro storage. When excess electricity is available, water is pumped uphill into elevator reservoirs. When electricity is needed, the water flows back down through turbines to generate power. Hydrogen is another promising option. Surplus electricity can split water into hydrogen and oxygen. The hydrogen is then stored for future use. Large-scale battery systems are also expanding rapidly. Some battery installations can inject power into the grid within fractions of a second, helping stabilize electricity supplies almost instantly. Today, wind turbines alone cannot guarantee the energy needs of an entire nation. Not because they lack power, modern turbines are already capable of producing enormous amounts of electricity. The real challenge lies in storage and grid management. But those technologies are advancing rapidly. As battery systems improve, hydrogen infrastructure expands, and power grids become smarter, wind energy will play an increasingly important role in powering our world. The giant machines that once looked like simple spinning fans on the horizon are becoming one of humanity's most important energy sources. And this transformation is only just beginning. If you enjoyed this video, don't forget to subscribe for more fascinating deep dives into the incredible technologies shaping our future. Thanks for watching, and we'll see you in the next one.